Hey guys. All right, so this week there's going to be two different lessons. They both are about evaluating limits, sort of continuing in our limits theme. So here are some properties and I'll show you why they work. So the limit of constant is the constant. So if you take a look at this picture, 11 is a constant. Here's what the graph of it looks like. It's a horizontal line. And if I'm approaching any number, right, I'm approaching 5 here. Doesn't matter whether I'm approaching 5 or 8 or 59. This is a constant. There's nothing else that this can possibly equal but 11. All right. And then here's another property. Again, you can take a look at that. If you're taking the limit of x, as x approaches c, it's going to equal c. So let's take a look at what that looks like. This, if you graph it, is this particular line. This is y equals x. And if I'm trying to approach -2, it kind of makes sense. Oh, look at that. The function actually equals -2. There's no holes, there's no jumps, nothing. Okay, so let's take a look at the next one. So if you have x raised to a power, and then x is approaching c, your limit ends up being x raised to c. And here's what this looks like. This is x squared, right? Standard parabola. And if I'm approaching 3, graphically, you know that that equals 9, but that's also the same thing as if you changed, right? If you just plugged that in and got 9. Okay, so what did all these have in common? It's continuity, right? If your graph is continuous at the point you're trying to evaluate the limit, then all you have to do, this will be the easier of the two lessons. You just have to do direct substitution. So look at this. I don't have a graph of this, but that's no big deal. I know this is a line. If I did graph it, it would be a line. All I have to do to evaluate this is to plug in 3 in for x. So this limit equals 15. Okay. This. Now, if you think about what the graph of this looks like, yes, it does have an asymptote at -1. Okay. The graph as a whole is not continuous. However, at 2, there's no asymptote. It's continuous at 2. There's no holes, there's no jumps. It works just great. So if you do direct substitution, your calculation is going to look something like that. And the limit is 1. Okay, let's keep going. Okay, so you know what a sine graph looks like, right? A sine graph is just a wave. It is continuous, no holes, no jumps, no nothing, no asymptotes. So I can do this by substitution. All I have to do is plug in pi in for the x value. And so I just give myself a little hint here. Pi ordered pair is at -1, 0, and the sign there is 0. So this limit equals 0. Okay, sort of the same situation here. Maybe you don't know that this is continuous, but you can always check as far as limits first by doing direct substitution. Okay, if you plug the number in and it doesn't give you any issues, right? If there's no zeros in the denominator or negatives under a radical or things like that, right? If it doesn't cause any problems, just plug it in. Direct substitution is always going to be your first line of attack. So if I put 0 in here, the tangent of 0 is 0. 0 over anything equals 0. There's your limit. Okay, and then this one, again, you can pause your screen if you need to take a really close look at this. All it's saying is that if you have a composition of functions, you can either do the limit after the composition or you can do the limit of just the first function. It doesn't matter. So if you look at these, you could do the composition and then see if 3 works. Or you can just remember that you can do the limit of the inside function first, which I'm going to attempt by direct substitution, which works. If I put 3 into the f function, I get 10. Then I put 10 into the g function, and the answer to this problem is 100. All right, I hope that made sense. I have a worksheet for you. I'm available for office hours. Schedule an appointment. Miss you guys.